Bismillahirrahmanirrahim. Dear viewers, today the topic of our discussion is conformational isomerism. Before we start the topic, just remind that stereoisomerism, a subtype of isomerism, has two main types. One of them is the conformational isomerism and second one is the configurational isomerism. We will discuss the configurational isomerism in the upcoming lectures, but today our focus is on conformational isomerism. You see that the conformational isomerism is again divided into two main types. One of them is the eclipsed conformation and second one is the staggered conformation. We both of types we will discuss in detail today. As you see that conformational isomerism is a type of stereoisomerism in which different isomers are formed by the rotation of a sigma bond. You see that here this is sigma bond is being rotated, as a result of which whole of the group attached to this sigma bond is rotating and thus new isomers are being formed. You can clearly watch it in a different angle seen from a front view of the molecule. You see that different isomers are being originated in this molecule. We will see all these isomers in detail. These isomers are also called conformers or rootamers. Let's see these conformers in still picture to explain more clearly. For example, in case of ethane, a 2-carbon molecule, you see that here the molecule is shown in Newman projection. This is the front carbon and the circle denotes the back carbon view. To distinguish between the different hydrogens of the molecule, they are shown in different colors. Especially focus on these blue colored hydrogen. You see that when all the hydrogen they are in front of each other and they hide each other. This form is called eclipsed or syn conformation, in which we take the angle for reference as 0 degree. When the molecule, the sigma bond, which bonds to carbon atom, is rotated at 60 degree angle, a new form is obtained, and this is called gauche isomer. When this hydrogen is rotated up to an angle of 120 degree, the form that we obtain as a result is called eclipsed partially form of the conformation isomerism. And when this hydrogen is at 180 degree angle, it forms the staggered conformation. Now if hydrogen is turned more from this angle up to 240 degree rotation, this brings this hydrogen at this position. Both these compounds, this one and this one, will be same. So they are not mentioned here in this case, but we will see in further coming forms this also in detail. Now the same molecule is shown in Sahor's configuration and wedge dash configurations, as well as in three-dimensional models. You see that in the eclipsed conformation, both of the hydrogen at above and below of the plane of are there in front of each other, and they hide each other. So the form is called eclipsed ethane. This is very clearly visible in this 3D molecule. Whenever you, for each angle you rotate the molecule, you will get the same configuration and the same shape. So this one is the eclipsed ethane. But in case of staggered ethane, you see that due to the rotation of this sigma bond between two carbon atoms, when this rotates, it brings the up hydrogen at downward position and downward hydrogen at upward position in the manner that no one hides the other hydrogens. As a result of which we obtain the staggered ethane. You see in 3D models that when you rotate the molecule, the backward hydrogens are also visible, which is in contrast with the eclipsed ethane, where you can see the back hydrogens when rotated at uh, front to view from front view of the molecule. So this is the staggered conformation. Of course, when the eclipsed conformation, the atoms are at one line to each other, so there is more repulsion. So this makes this form a little unstable, and this form, which is the staggered one, is more stable than the eclipsed form. The energy difference between the two forms is about 2.9 kilocalories per mole or 12.1 kilojoules per mole. You can see it from the graph that the eclipsed forms have the higher energy and are placed at higher position in the graph, while the staggered form, they have a lower energy and are placed at lower position in the graph, so they are more stable. This destabilization is due to the torsional strain, as I already explained. And to understand what is this torsional strain means, you see that in these two diagrams, the torsional strain and van der Waals strain both are shown. The torsional strain is the destabilization due to the repulsion between pairs of bonds caused by the electrostatic repulsion of the electrons in the bond. So, torsional strain is caused by the electrostatic repulsion of electrons in the bond, while in case of van der Waals strain, the destabilization occurs due to the repulsion between the electron clouds of atoms or groups. So all of the groups are responsible for the van der Waals strain. And this occurs when atoms or groups are too close to each other due to the electrostatic repulsion of the electron. So this strain results in the um, stabilization of the molecule, and here the stabilization is more in case of the staggered uh, form of conformation. Now, in case of propane, you see that there are two possible conformational isomers of propane. Again, the eclipsed and the staggered conformations. Both are shown in two-dimensional diagrams and in three-dimensional models in this lecture series. You see that in eclipsed form, let this methyl group at above position, and these two we are going to see when they are rotated, they hide each other. The front hydrogen hides the backward uh, hydrogen. So this is the eclipsed form. While in case of the staggered form, when we see and rotate the molecule, you see that no hydrogen is covered by the other hydrogens of the other carbon atoms. So it means that this form is the staggered form of the molecule, and obviously this form, the staggered form, is more stable and almost 3.3 kilocalories per mole or 13.8 kilojoules per mole. Now we come to the conformational analysis of N-butane. They are more clearly shown in two-dimensional diagrams. You see that the N-butane can have following 6 conformational isomers. When the angle is at 0 degree, we have named this as A form. So both are in front of each other. These are the middle carbons. These are the terminal methyl groups in the molecule. This one is the carbon number 1, that it be carbon number 1, and this one, the circle shows the carbon number 2 in the chain. Means carbon number total there are 4 carbons, and these two are the middle carbons, carbon number 2 and 3, which are joining the molecule in between. So when both the methyl groups, where we are taking them as a reference, they are at 0 degree, this form is called syn or eclipsed form. 0 degree with 0 degree angle. The second form is the Gauch, where the methyl group is rotated at 60 degree angle, and the form is called Gauch form of the conformational isomerism. Third part is the when methyl group is uh, rotated up to an angle of 120 degree. You see that a methyl group is at 120 degree, and this form is called eclipsed form. In the D structure, the methyl group is at 180 degree rotation. Then comes the A. In this case, This E resembles to C. Both are same except for that one of the form is uh, at right side and in the other the methyl group is at left side. And the F is again a gauge where the angle of rotation is 300 degree. So this form resembles with the B form of the series. Although they are named same, the B and F both are called gauge form and C and E are called the eclipsed form, but actually they are not same. They are mirror images of each other. We will discuss this phenomena in our upcoming lectures. And this is for simplicity because today we have to focus on conformational isomerism only and not on the mirror images of the molecule which are being formed. Now we take each of the molecule in 3 dimensions. Let first of all discuss the A, which is called sin. This form is well shown in wedge dash diagrams and Fisher projection as well as Newman projection methods. And to clearly explain the molecule, we have a 3-dimensional molecular structure 2 in the screen. You see that this is a 4-carbon chained molecule. All the carbons are in a straight chain, so this is N-butane. In A, carbon number 2 and carbon number 3. You see, when I rotate the molecule, all the hydrogens eclipse uh, the other hydrogens. So it is eclipsed form too. But we are calling this as a syn conformation. These are the terminal methyl groups and we are taking these two carbons under our study. Carbon number 2 and carbon number 3. And you see that in the syn configuration, both the methyl groups are at 0 degree to each other while the other are hiding, the hydrogens are hiding each other, and this makes the geometry of the molecule like this and is called syn conformation. Now we come to the B or the gauge conformation. In this case, you see that the methyl group is rotated at an angle of 60 degree from the previous position, as a result of which we obtain this molecule. Now see here in 2-dimensional diagrams and 3-dimensional model, you see that one of the methyl group is rotated at an angle of 60 degree. This reduces the torsional strain a little bit, making the molecule a little more stable than the previous version. you rotate the molecule at any angle, you will get the same result. The hydrogens are also not hiding each other. Now come to the C, the eclipsed conformation. Remember, in the C or eclipsed conformation, the methyl group is rotated at an angle of 120 degree. So, as a result of this, you will get this configuration. The carbon number 2 and carbon number 3 and one carbon is at its own position and second one is rotated up to an angle of 120 degree. This makes the molecule more stable than the previous version, as the strain is more or less than the previous form. Now the D or anti-conformation. Remember that in D or anti-conformation, both the methyl groups are at anti-position to each other at an angle of 180 degree. As a result of which we get this isomer. You see that the carbon number 2 and carbon number 3, the middle carbons, and carbon number 1 and carbon number 4, they are at anti-position to each other. Very clearly visible when you rotate the molecule to any side. Because the strain is least in this case, so this form must be most stable form of the series. And you will see the energy diagram to confirm this and to understand this more clearly. Here is the energy diagram for the molecule. You see that D has the least energy and it is the most stable form of the series, while B and F, remember B and F, E and F, the gauge forms, they comes next in the series, and then C and D, C and E, because in a C and E, hydrogens are at same level and they have a strain too, which is causing the molecule to be less stable. And in case of A, which is the least stable form of the series, the energy is highest. This is because both the groups and all of the groups are at same level, same position and have maximum strain, which is causing the molecule to be unstable and to have a highest energy in the series. That's why the A or syn form is least stable and the anti form is most stable form of the series. So dear viewers, this is all about the conformational isomerism, which is resulted due to the rotation of a sigma bond, a rotation in the molecule, We will discuss this form of isomerism in the cyclic system in our next lecture. Cyclic system will be our next topic. Thank you.